Welcome back to your physics notes with Mr. Yale. So today we're going to talk about the introduction to motion. So when we talk about motion, what you really want to keep in mind is the whole purpose of what we do in physics is to try to explain what's going on around us in a way that is sort of repeatable, observable, and that you can prove right or wrong. So the reason that these are so important is because these are values that we can observe in nature. So physics is about observing things and explaining what happens. Well, displacement, our first thing we're going to really talk about, this is an observable quantity. Now that's important. We can observe it. We can measure it. What displacement is essentially your change in position. And we use delta, which means change. And you could say you had change in the x position, or you could have a change in the y position, or some other position, however you define it. But that's what it is. Displacement is change in position. Now, what's very often confused is people look at distance traveled and think that's displacement. Distance traveled is a little bit different. So this is how far, example, would be like number of steps taken. So that's distance traveled. But change in position, an example would be position final minus position initial. Okay, so that would be your change in position. Let me give you an example. Let's say you're on your way to school, and this is your house, and this is your school. And let's say you drive over here first. You go down this street, and you stop at Shipley's, and you buy a donut. Then you go over here, you stop at your friend's house. Let's call him Jim. It's Jim's house. You stop at Jim's house, then you go to school. So your distance traveled would be all of these added up together. This is the number of steps you take, or the distance your odometer in your car says you travel. Whereas a vector drawn from here to here would be your displacement. It doesn't matter how far you actually go, how many miles you drive in your car. All that matters is where you start and where you end. That's your displacement. So that's the difference between those two things. Okay? Now, again, the reason that's so important is because displacement is measurable and observable. You can measure it. Now, once you measure your displacement, you can look at your velocity. Okay? So speed versus velocity are two things that are very often confused. We've kind of talked about this already. Speed is how fast. It's how fast you go, whereas velocity is how fast you go and where you go. Okay? It's your speed plus direction. It's very important. Okay? So velocity is a vector, so displacement is a vector. Velocity is a vector. Those are both vectors. Distance traveled is not a vector, it's a scalar. Speed is not a vector, it's a scalar. They just have a magnitude, they don't have a direction. Okay? So to find your velocity, you can calculate it, and it is your change it's your displacement divided by how long it took you to do that displacement. Okay? So you can see that once you observe this, you measure your displacement, you can calculate your velocity. Okay? So they're related to each other in that you can observe this, you can measure it, then you can calculate your velocity. And once you know how fast something's going, and which direction, that's a way to describe its motion. Now, after you do that, you can then calculate acceleration. Acceleration is very tricky, okay? So acceleration is often confused. A lot of times people think acceleration and velocity are the same thing. They're not. Acceleration is the change in motion. It's very important. So it's the change in motion. You can calculate acceleration. It's equal to the change in velocity over the change in time. It's how long it takes for your motion to change by a certain amount. So your motion can change by a whole lot in a very small amount of time, give you a big acceleration. It can change by a whole lot, but over a very big amount of time, it would be a smaller acceleration. So what's interesting about these things is that when we look at physics, these are both important, velocity and acceleration, but they're kind of important for two different reasons. So we can measure velocity. Velocity matters. It's important. But acceleration is kind of a more explainable thing. Okay. So for example, if you look at the velocity of an object, let's say you are sitting on a bus. This is a horrible bus, but let's draw it anyway. So this is me on the bus. This is you on the bus. And I look at you. Let's say the bus is moving with a velocity v to the right. If I look at you, it doesn't look like you're moving because you're on the bus with me. We're both moving to the right with a velocity v. But if you have someone else standing over here and they look at us, it looks like we're both moving with a velocity v. So the reason this is important is because velocity is kind of an arbitrary value. It depends on who's observing. So from my perspective right here, it doesn't look like you're moving. From this guy's perspective, it looks like we're both moving. Now, if either one of the people on the bus look at this guy, it actually looks like he's moving with a velocity v. Okay? So velocity can be kind of tricky because it depends on the observer. Acceleration, though, doesn't depend on the observer. If I'm watching you on the bus and your motion changes by a certain amount, I can observe that and measure it regardless of what your initial velocity was. I can see the change in velocity. This person watches the exact same event. If they measure the change in velocity, they should get the same thing that I do on the bus. So velocity depends on the observer. Acceleration does not depend on the observer because you're looking at the change in the velocity. Okay? So it seems like it might be a little arbitrary and that won't really matter very much, but in reality, when you're looking at physics and you're looking for the deepest explanation you can get, something like that can actually matter quite a bit. Okay, so now those are your basic definitions of those three things. They can be applied in many ways. We'll use them a lot. Let's take a quick look at a couple example problems. So these are both on your problem set. Which object moves with constant non-zero acceleration? So you have object A, object B. So constant non-zero acceleration is the key here. Okay. So if it's constant, that means the acceleration is not changing. If it's non-zero, it means that it must have an acceleration. So our object is accelerating, and it's doing so in a constant manner, meaning whatever the acceleration is, it's not changing. So what does acceleration mean? Well, acceleration is change in motion. So that means my motion is changing in a constant manner. So let's look at these. Object A, it has an initial velocity of 1 meter per second, and it does that for a second. But what do you notice about right here? It's a flat line. So that means at 0 times 0, it's 1 second. At half a second, it's 1 second. At times 0, it's 1 meter per second. At half a second, it's 1 meter per second. At 1 second, it's 1 meter per second. So over this time, my velocity did not change. Now, all of a sudden, it drops down to negative 1 meter per second, so I start moving the opposite way. So it changes here, but then it stays constant at negative 1 meter per second. So this would not be constant acceleration. The acceleration is nothing right here. Bam, all of a sudden there's an acceleration, and then there's no more acceleration. So that would not be constant. Now let's look at object B. If you look at the velocity, which is over here, I start out at 0. A fraction of a second later, it goes up by a tiny bit. Fraction of a second later, it goes up by a tiny bit, up by a tiny bit, up by a tiny bit, up by a tiny bit. And you can see that my velocity all along this, every time, has a different velocity, and it's going up by a set amount. That would be an example of constant acceleration. My velocity starts at 0, and then it changes, it changes, it changes, it changes. So it has an acceleration now, but is it constant? So if we look at this, what would a constant change in v over change in t look like? If I was to graph this, if my acceleration, sometimes just picking an easy number is the best thing to do. So let's say my change in velocity over change in time, which is really my slope of this, is a constant value. That means if I go up 1 and over 1 in the first fraction of time, I would go up 1 over 1 in the second one, up 1 over 1, up 1 over 1, up 1 over 1. What I should get for this is a linear function, okay? So this one is not constant either. It's accelerating, and it's always accelerating, but that acceleration is always changing. So I would say neither A or B, okay? So this one only changes here. during that time is when I have an acceleration. This one is always changing, but it's not constant. Okay, let's look at another one. So now vectors v1 and v2, which are over here, have equal magnitude, so those arrows are the same length. The vectors represent the velocities of an object at times t1 and times t2. The average acceleration of the object between time t1 and t2 is what? So if I start with a vector in this direction, okay, so let's say that's v1, and sometime later I have an equal length vector, but it's in a totally different direction. So the question is, what do I have to do to this vector to turn it into that vector? Because remember, what they're looking for is average acceleration. Average acceleration equates to your change in velocity. Okay? So how did my velocity change? What do I have to do to this one to get to this one? The easy way to do this is to use the head to tail method and add your vectors together. Okay? So if I start with this velocity right there, that's v1. Sometime later, I have v2. Sorry, that should be a 2. So the question is, what do I have to add to this one to do the head-to-tail method to get right there? This is my change in velocity. So which of these agrees with that change in velocity? North? Well, it's going north, but it's also going west. West? So it's also going, I'm looking for northwest, directed north of west. So that is your answer. Okay? So remember, acceleration, change in velocity. Adding vectors, you can use the head-to-tail method. What do you have to add to this one to get this one? The easiest way to do it is like that, to make a triangle. All right? So that's the first video in your series of motion videos. Thank you very much.